Hey everybody, today we'll do another video and today we will do another video on convolution. Um, we will do a convolution, right, using the graphical method, right? So, okay, so let's say that we have a two function represented by each, two signals, right? Represented by each, each function, each signal represented by its um, graph, right? Or you can say each signal represented by its function, but it's, the signal itself is in the graph, right? Let's say, for example, that that you have two signals. You have f of t is equal to is equal to is equal to e to the at when t is greater or equal to 0 and is 0 for all other, or you can say when t is less than 0, right? And let's say that you have this type of function like this, right? Then, and this is a piecewise function, right? Piecewise, which means it's piecewise continuous, right? So, and let's say that you have another one that is that the other one is g of t is equal to u, actually u, not mute, u of t. Okay, and let's say that and let's say, for example, that the graph for this guy is something like this, right? Let's say, for example, that the graph of this is a decaying exponentially like this, right? Okay, so let's say over here the value is whatever, right? I mean, just doing a general, right? It's a good thing to specify something, right? I mean, that's one up there. Now, let's say, for example, that we have u of t, this right here, g of t, it is a whatever, right? So let's say, for example, this is just a continuous, right? It goes to infinity, but normally we try to cut that off, right? So, and then both of the function of t, right? And what I mean cut it off, I mean that we don't calculate anything usually go to infinity, right? Because God can do that, but we cannot do it. I mean, those that you believe in God, right? If you don't believe in God, then probably you don't care, but this is a conservative engineering academy, so I believe in God. So, okay, so let's say, for example, this goes to infinity, right? But we can cut it off at some time, right? Somewhere over there. Who cares, right? Right there. And also the value of this is equal to 1. Right. But normally the u of t, the function is equal to 1, right? At starting at 0 and going from 0 to infinity, it is 1. That is the unit step function. That's why it's called unit step, right? Now, what I can do is the following. So let's say, for example, that we want to do a general, this is a t. Um, general calculation of this, right? Now we calculated that when t is equal to this, right? Right? When t is this, then it's less than 0 in this function, right? And in this case, when t is equal to 1, when ut is equal to 1 when t goes to infinity, from 0 to infinity, right? Now, this is what we'll do, right? So let's say, for example, you have f of t convolved with g of t, right? Now, what I will do, right, in this case, is write that is going to from infinity to infinity on the convolution, right? Obviously, when normally we start engineering, we start at time is equal to positive values, because from negative values at time, I don't know any system that starts at negative values at time. I don't know anything that starts at negative. No, I mean, time starts from zero time to, right? So basically, the normal definition for this, right, is like this. Okay, so when this is tau, right? This is tau in f of t minus, okay, so convolve with g, right? So convolve with g of t minus tau d time, right? Now, when this goes to infinity, okay, so again, this is the normal definition, but mathematicians, right? Engineers and mathematicians, they do things a little different. In engineering, we try to use more common sense, right? Of t at infinity negative doesn't make any sense. T at infinity positive, I guess it can make sense in the analytical purposes, but again, we cannot just do infinity, right? It's defined, it's two terms, either converges or diverges in the mathematics, right? Converges mean that it converts to a specific value. That's what we want, right? Engineers, we want numbers, we want results. Converges. Diverges mean that it is either go to infinitive large or infinitively small, which at the end of the day, it doesn't give me a number. It just gives me an analytical idea of look at things, but not necessarily a number that I can actually say this is what look like it is and this is what it is, right? It to kind of margin things in this, can you say the smaller, errors that we human being can make, right? I guess. Now, and this is what happened. And we'll try this real quick. We will try this with a calculator, right? So, okay. So now what I will do is the following. So this is ut, right? And we know that ut is equal to 1, right? It's starting from 0 to infinity. The ut, the value is equal to 1. Right. Now, what I will do is I will swap this. Actually, it's fine as it is. It's fine. It's fine as it is, right? So now, at the moment, I will replace this guy right here, right, with okay, so what I will do is write the integral and replace this function, this piece right here, right, with, I will replace f of t with that, right, and I will replace u of t with this, right? Okay, so, and we know that this guy is equal to 1, right? We know that this guy is equal to 1, but I don't want to confuse anybody, so just put the 1 over here, right? That is belong to the u of t. Okay, so now we do f of t convolved with g of t is equal to, now we're going from 0, right? Less than 0, we don't have anything. So technically, we don't even have to calculate, right? But for the analytical purposes, just to see if this makes sense, we can actually do infinity to infinity, right? Now, but as you know, as you see, you can actually see it right now from here based on this, that this is nothing but when I come in and I move this, right? So let's say, for example, in the graphical, so I do, right? So what I will do is replace this t right here, e to the minus a tau, right? The t is replaced with tau. And what is the value of u t, right? U t d tau. What is the value of ut? The value of ut is simply 1, right? So replace that with 1. Okay, so then we analyze it, right? So when I'm convolving this guy only exists in positive values, right? From 0 to t to infinity. This guy is going to exist somewhere. You can see this going to decay, right? Like anything else, right? It's going to decay. Now, it doesn't matter that this goes to infinity, right? This can go to infinity large, but if you see that this, once it exits this, the convolution is going to be not valid. If you go from negative right here, right? If you go to the left, it's going to be invalid. If you go to the right, past this point, right? This right here is going to be invalid too. Okay, so let's say, for example, that I do a graph right here. And I said, okay, so I say that this is my decaying function, right? Maybe right here. Right? So my decaying function. So my decaying function right? And this is my u of t. This is my u of t, right? So what I did, I put this, I slide it a little bit to the left, and all the way to the left, right? Over here, the t is positive, is negative, right? All right, so time is negative. If you can see that this is the only area that counts. I'm taking the integral of that, right? To the left, that don't care. To the right, I care to a certain point, right? Keep sliding to the right. And that's the whole point. Keep sliding to the right. When this guy is covering the whole area up to here where, this is eventually touching zero axis, which is converging to zero. And that's why it's important when do the convolution that it has to converge. If it doesn't converge in engineering, it doesn't make a lot of sense, right? So what makes this converges is this e to the t. E to the t is decaying, so eventually this can be, off the board. If it is got to infinity, it doesn't matter. It's already past the value where the area that we're looking for, right? Okay. So let's say, for example, that we do that. And we will solve this in general. We're not going to add any values, but we will analyze something. When I say not generate values, I'm saying not defined values of time. Right? That's what I'm trying to say. So, this is f of t. This is g of t. Okay. Now, let's look at this. Now, if I integrate this, what do I get? Right? So I integrate this guy, right? I integrate this guy. Now, if I integrate that, the integral of that is going to be just the integral of that, right? So I multiply that and take the integral of it, right? So multiply that, which is technically from 0 to, right? So let's start from 0 now, right? Because we know that it's going to be existing only for value greater than 0 to infinity. T greater, right? It goes to infinity, but again, we're analyzing where this is being canceled, right? Think about silencing a signal, right? Or maybe canceling people. Democrats are easily, very slowly cancel culture, the conservative, right? Eliminating the free, kind of slowly but surely, they want to get rid of the free speech. Cancel culture. Think about silencing a signal, right? So when you silence a signal, the signal is high, and you use this a lot with filters. When you're filtering a system, right? But let's put the Democrats, right? Let's say that in 1945 we have a lot of free speech, right? So now we in 2020 we are here, right? The Democrats are slowly silencing, right? Cancel culture. It is slowly decreasing on the freedom of speech. It is one of the things. This is engineering academy, but I like to kind of put stuff like that, right? Like we can call this, like I said, we could call that d tau, or the tau value, we can call it fake book, and we call it the t, right? The t value that we're generating eventually, right? This t right here, the t that we're keeping, we call that the t. Well, I call it, I don't know about you, but I mean, true social. Right. So, okay, so Facebook is equal to tau, the one that we replace. T is equal to true social, right? We fight that, right? That concept, right? The conservatives still kind of try to, I would say, just, trying, even though that it's purely discriminate, it seems like it's going that way, but again, that's that theory, right? That's Anyway, so now let's do this. Let's take the integral of this, right? So this is e to the minus at. All right, so a tau d tau. Okay, so take the integral of that, right? It's going to be 1 over a negative, right? And it's going to be the following. So it's going to be, if I take the integral of this, so I move that down, right? So it's going to be a, so it's going to be e to the a tau, right? So, and then it's from 0 to t. Okay, so because I am defining t at this, right? So t is going to infinity, right? I don't know, the Democrats will take to infinity to kind of cancel us, but he might, right? I don't know. I don't think so. I think Jesus is coming before they cancel us. But anyway, so this is what is going on, right? So let's assume that t, this is going to infinity, right? Or at least approaches infinity. Infinity what? Now, when I substitute these values, okay, so when I substitute that value, I get the following. So I get negative 1 over 8, right? If I plug in 0 for this one, right, it's going to be any number, right? So e to the, okay, so e, okay, let me do something right here. Let me replace that because I already I'm saying a t plus, right? So when t goes to infinity, this guy right here is going to be equal to negative, actually just 1. This guy right here, if t is going to be 1, right? If t is 0, then that is equal to, t is 0, that's equal to 1, right? Minus, right? Now, That is one of the values, right? Now, actually, no, I don't want to do that. Now, let us do when t goes to when t is greater than 0, right? This is nothing but you still keep the same thing, right? So it's going to be the same exact things. A with the t when t greater than 0. Now, what do I do? As you can see that right here, when t is when t goes to then this is nothing but the integral. This integral is equal to, when you evaluate that, right, at 1, right? So, right, so technically it's a negative 1, right? Because you're evaluating at that a negative 1, right? So it's negative 1, right? But then you multiply this, right? And then you do this at infinity. So this becomes 1 it becomes negative 1 plus e the a t. But remember that this is still being multiplied, right? That is still being multiplied through, right? So that negative still being multiplied. Negative, right? This look like 9, right? So when that is going to infinity large, I can flip this, and this becomes what? This becomes nothing but, if I move this across, right, multiply this, right, and move, do it as it is. So basically it's 1 over a, and I just distribute the sign inside. And it's equal to 1 minus e to the a t, negative a t. No, you don't even have to put the bracket parenthesis in this case. Okay, so now let's analyze this. Let's analyze this. Think about, in engineering, in electrical, specifically electrical engineering, this look like an RC filter. RC circuit. If you're familiar with RC circuits, when you have a capacitor either charging or discharging, you can actually see that this is going to be a slowly charging capacitor. If you go like this, it's going to look like this. So it's going to be, if you think about it, right? A 0, right? Okay, let me do it so you can actually see it, because this is going to be important. So let's say, for example, at 0. I think out of everything, this is the most important to analyze. Okay, so R0, this is going to be equal to 1. 1, and then 1 minus 1 is 0. Okay, so at 0, in other words, we transform the function from being a decaying function to kind of increasing, slowly increasing function. But remember that that's going to also, the most beautiful thing about this is like, it also depends on the value of A. Like, for example, in this case, so let's say, for example, right, at 0, it doesn't matter what the value of A is, right? So let's say, for example, A is 1, 1 minus a 0 power is 1, so it's equal to 0. So we are here. Right? And we are here. Nothing, right? Now, let's change the values. Right? Let's say, for example, that A equal to 0.5 and T is equal to 1 second, right? 1 second. If you plot that in the calculator, say T is equal to 0.5. Remember, when I replace that, that is going to be equal to what? It's going to be equal to 1 over, so it's going to be equal to 1 over 0.5 E, right? 1 over 0.5, 1 minus E to the 0.5 times 1, right? When I do that, 1 minus E to the negative 0.5 times 1. Right. That's a very small value. It's slowly increasing, but we are about point right here, about point 0.20. So it's right here. So we are like this. We know at this value right here, at 0 was 0, but we're slowly increasing. So if you keep going, you will just like this. Eventually, it's going to look flat. It's going to reach a certain value, and it's going to keep fluctuating between 1 and 1 and change, and it's going to be very slowly increasing. And that is in when it reaches the flat, right? When it reaches this peak, right here, we say the capacitor is fully charged. Let me change the value of T, keep the A constant, and change the values of T. Now, let's look at 0.5 times 1 minus E to the negative 0.5 times 1.5, right? I added a little more. It's increasing a little bit. So now we are 26. We are here. And it's going like this, and eventually it's going to be like this, and it's going to be closely, but like I said, it's going to, and it's not easy to draw this, but it look like this. Look like this. like this. So it goes like this, like this, like this, like this. So at this point, think about it. So we're increasing the values of t, right? And let's say, for example, that I do one. Let's say, for example, I do one with 0.5, 1 minus, right? Minus e to the minus 0.5 times 2, right? I went to t is equal to 2 seconds now, right? T over here was so in the first one, t was 1, right? So t is equal to 1, was right here. T is equal to 1.5, right? We are here, 1.5, t is equal to 1, and over here we are t, I would say very close, but not, because again, this is 1, so this t is equal to 2, right? So a t is equal to 2. It's reaching. It's very slowly increasing, though. It doesn't increase by a lot. But now I got 0.31, which is very close, and I cannot, unfortunately, it's going to be rough for me to write those numbers. But the first number right here, matter of fact, I will just do this in this little space that I have right here, probably is even better. So, okay, so let me just do it with this. All right, so at this point 0, right? And then at this point, we say that it's point. Let me just do this and this. It's point to 0 right here, right? Like this. But it's slowly increasing. And over here is 0.26. 0.26, right? And then, but this eventually will be like this, right? So it would be like this, like this, like this. But again, these numbers are very small. Like at this point, see right here, at t is equal to 1. So t right here, this is a t, right? T is 1. Right here, t is 1.5. And we actually reaching, like, it's not even, like, it's going to be probably 1 is right here. I mean, yeah, so, right? But then, right? And then, we can just move this up a little bit. Again, this is not up to scale, right? 0.26. Right. So, and then it's continually until it gets flat. Then we know the capacitor is charged. So the question is, what will be the value of T when the capacitor fully charged? It's called a time constant, which that T is also defined by RC, the value of the capacitor times the value of the resistance, giving you the time constant. But 0.5, like let me just do another one. So 0.5, 1 minus e to the negative 0.5 times, let's say for example, times, okay, so let me just put the value over here. Apparently it's 0.31, slowly increasing. And eventually it gets very close to 1. So let's say, for example, and now T is 4, just to see. Let's make it bigger on T. At T is equal to 4, still, it's a very slow increasing. Very slow. So right here, T is equal to 4. So it's 0.43. See? So in other words, this graph, it should look, when you condense the numbers, by the time you get to 1, T is going to be very, very large, right? So at this point, T is already equal to 4. See how this is working? And this is what I want you to analyze, right? So, because this is, important. So at this point, T is equal to 4, right? We tried it at 4, and it's still around. In other words, it's very slowly, like that. At the moment, eventually it's going to get flat, right? But again, you cut in these values, right? You're making the values of T large and keep it. And also you can play with it. You can make the values of A larger, and this will change too, because technically, yeah, so it's going to change eventually. So like I said, but A doesn't change. A is treated as a constant, and then you change the value of T. When you change the values of T, then it's going to get flat and flat. It's going to get flat, which means that we actually get in the exact value when the capacitor is fully charged, right? So that's how we analyze the systems. And it's a very unfortunately, we cannot see like a very clean graph because you need graph paper to do this. But I'm just showing here that at this moment, it's not even like over here at 4. It's not even, not even the half. So this should be more like increasing a little bit, but at the same time, it's very slow. It's very slow, right? So yeah. So this has been the video for today, and I hope you learned something. And I'll see you in the next video. Thank you for watching.